right, good morning, everyone. It is a great pleasure to have Roeland joining us today. Roeland is a very good friend and collaborator of mine. And for those of you who don't know him yet, he is actually an alumnus at CQIQC, formerly advised by Juan Calasquilla, a faculty member who used to sit at CQIQC and moved to ETH currently. So after completing his PhD, Roeland moved to his postdoctoral fellowship at CCQ of this Flatiron Institute in New York. Although Roeland is, perhaps best known for his seminal computational physics works, today he's bringing us something different, something deeply theoretical and, even more intriguing to me. That is a classification of dynamical Lie algebra. And let's give him a warm welcome.
Hi, thank you. That's probably one of the nicest intros I've ever had, so that's very, very kind. Yeah, and I'm very glad to be back in Toronto and to present this work to you, which I did at the end of my PhD. And yeah, it was a really fun project because I'm not a mathematician myself, but I found a very, very good mathematician that helped me do this work, and I'm very grateful, of him and my other collaborators. So yeah, as the title suggests, this research or these projects are about classifications of dynamical Lie algebras. And for those of you who are not familiar with what a mathematical classification is, I think this isn't a reasonable definition. So a mathematical classification means that you've basically constructed a list of all the unique mathematical objects within a specific mathematical structure up to isomorphisms. And so as a very simple example, we have this type of classification, which was studied by Euclid in 300 BC, and he asked the question, how many convex regular polyhedra are there in 3 dimensions? And back then, he was able to give a conclusive mathematical proof that still holds up today, and he concluded that there can only be 5. So he was able to exhaustively prove that these 5 objects are the only convex regular polyhedra in 3 dimensions. So this is a very powerful statement because you've basically drawn a circle around a piece of mathematics and shown like, okay, this is the only thing that can exist within it. And if we now skip forward 2,000 years, math has developed quite a bit, and one of the sort of classifications that's central to our work here is this one by Cartan, which was done in the early 20th century, and it's a classification of the compact Lie groups. So Lie groups are they're groups that are smooth and differentiable, and they show up all over physics and mathematics. And Lie was able to prove also exhaustively that these classical groups, which are enumerated with A, B, C, and D, which I think most of you will know as like SON or SUN or SPN, that these are the only ones that can exist. And so he was able to prove that for any dimension, what these Lie groups can be. And this is a very powerful statement because it's basically a classification of continuous symmetry. So he was able to show that these are the only continuous symmetries that can exist in some dimension. And what is very interesting about this is that, again, skipping forward 100 years, people were able to use these results to classify physics. So this is a classification done in 2011 of all gapped symmetric phases of 1D spin systems, plus some other constraints. But it basically relied on the work by Cartan from 100 years ago. And I think the main point of this here is that, you can also use mathematical classifications to sort of bound physics. So you can draw a circle around, this is a type of physics that we can possibly see because we know that these are the possible types of continuous symmetries that can exist. And this is kind of the main inspiration for this work. So I am a physicist and not a mathematician, so I'm more interested in this picture on the right. And so this project, was sort of inspired by these ideas. So for the second part of my of the title, we're talking about dynamical Lie algebra. So I need to introduce some notation and some math. So maybe most of you know what this is, but the simplest definition of a Lie algebra is that it is a vector space that is closed under the Lie bracket. So if you have a basis of matrices, say for instance the Pauli matrices, they form a basis for all Hermitian operators. You can turn this space of matrices into a Lie algebra by defining this bracket, which is the standard commutator, and saying that, okay, if you take any two matrices, calculate their commutator, that will still be in my vector space, basically. Also, you should interrupt me if anything's not clear here, but I hope that this is somewhat familiar at least. Okay, so yeah, very simple example, and we'll keep coming back to the sort of the Pauli matrices, which hopefully you're all familiar with. But yeah, so a Lie algebra would be the Pauli matrices on a single qubit, and then we equip it with the standard commutator. And so if we take x, and z, then if we take the commutator, we get something proportional to y. And so y is also has to be in our Lie algebra. Yeah. So then what is the dynamical Lie algebra? Because that is the main purpose of this classification, is to classify dynamical Lie algebra. So this is something that lives more in physics land and not really in math land. And what it is basically you have some Hamiltonian, it can be very general, it can just be some sum of terms. And then the dynamical Lie algebra is basically the Lie algebra that you get when you keep taking nested commutators of all these things. So this thing can be extremely deep, but you basically keep taking commutators until you have seen every possible element that you can see. And that's when you have sort of closed the vector space under the bracket. And yeah, this is the definition of this dynamical Lie algebra. And so it's basically, yeah, the Lie algebra spanned by the terms in your Hamiltonian. And as a very simple example, again, we can consider this Hamiltonian where we have, it's a one qubit system or one spin system. We have a Pauli X and a Pauli Y with some coefficient. We calculate the commutator, it gives us Z. And then any other combination of commutators will give us either something that's X, Y, or Z or some linear combination. So we say that, okay, we found the dynamical Lie algebra, it's the span of these three things. And this is the familiar SU2 Lie algebra. Now, closely related is the dynamical Lie group, which is the thing that you get when you exponentiate the Lie algebra. It's not super important for this work to know sort of the details of this, but sort of the main idea that I want you to keep in mind is that if you know something about the sort of the dynamical Lie algebra of some Hamiltonian, you also know things about its dynamics. So if you exponentiate this Hamiltonian, you know that it will always have support in the group that corresponds to this Lie algebra. So if we have SU2 here, and we exponentiate some Hamiltonian that lives in SU2, then the dynamics, sorry, will always be in SU2, but then on the group level. So this sort of correspondence between the Hamiltonian and sort of circuits is something that I really, always keep in mind. So yeah, statements about Hamiltonians can be turned into statements about circuits, because you can imagine you have some circuit that's generated by a bunch of exponentials of generators. And so yeah, these sort of two pictures are complementary. Maybe if there are any questions here, now will be a good time if the sort of the math here is clear. Yeah.
How do you break down?
This is a very, very good question that I will get back to when we make some assumptions. Because yeah, there's obviously some choices that you can make. Like maybe you consider x plus y to be one term, and then you get something else than if you would consider them as separate terms. So this is a very good question and like a very important assumption that we have to make. Yeah. Do you have a question? Okay, so then why, like this is all nice math, but why do we care about this? So originally, these dynamical Lie algebras showed up in quantum control, because in quantum control, what you want to do is you have some system with a Hamiltonian, and you can change the Hamiltonian interactions over time. And what you want to do if you want to build a quantum computer or some sort of simulator, that you want to make sure that you can make some unitary that you're interested in. Like maybe you want to make a C0, and so then you need to tune these parameters so that you can make a C0. And in general, you would want to make any possible unitary. So in order for that to be possible, you basically need this dynamical Lie algebra, so spanned by sort of these terms in your Hamiltonian that you have access to. This needs to span SU2 or SU4 or SU8, because that means that you can make any unitary on that Hilbert space. And so, yeah.
So what do you mean that covers the whole SU2? You mean that the U for all if you take the image of T for all T, you get all that specific, what the cover means?
Yeah, I guess it means if you take an infinite amount of time, you could reach any point on the group.
I see.
Yeah.
Like the image is the whole S.
Yeah.
Yeah.
Yeah. Yeah. And then sort of, if you're more familiar with quantum computing things, the sort of same picture applies to, or like you can think of having like universal gate sets. So if you have these gates, then you can make any unitary that you want. And this is kind of the same idea as this picture here, although this is on the group level, this is on the algebra level, but again, they're kind of complementary views. So yeah, you can imagine maybe you have a gate set that doesn't actually allow you to cover all of SU2. And that basically means that the generators of your gate form a Lie algebra that is not SU2. So yeah, so sort of understanding, given a Hamiltonian, what is a dynamical Lie algebra, allows you to make statements about what kind of dynamics can I have, what kind of circuits can I have. So it's good to know. Then there's some like very sort of, if you zoom in on particular types of dynamics, there's this very neat result from the early 2000s that says that if you basically have a circuit, or if you have a Hamiltonian with a very specific structure, such that this dynamical Lie algebra is polynomial in n, so it doesn't become exponentially large, then you can efficiently simulate observables in the Heisenberg picture, which kind of intuitively makes sense because you only have a small amount of degrees of freedom that you need to keep track, but then there exist efficient algorithms that allow you to simulate this. And this is true for free fermion systems or match gate circuits or the transverse field Ising model in 1D. These are all sort of equivalent things. And so people have shown that for those types of systems, you can get basically very efficient quantum simulation algorithms in your classical computer. And so knowing which dynamical Lie algebras are polynomial in size, aside from these ones that we already know, I thought was a worthwhile endeavor, like trying to understand, are there more out there than the ones that we already know? Now, the bane of my existence during my PhD, barren plateaus, for those of you who've worked on variational quantum computing, this is this result that if you try to do some variational optimization through some circuit, your gradients will vanish exponentially in the system size. This is basically a statement about the dynamical Lie algebra of your circuit. So you see here that the variance of your gradients scales proportionally or inverse proportional, or it's proportional to the inverse of the size of the dynamical Lie algebra, which can be exponentially big in the worst case. And this basically means that, if this thing is exponentially big, you're going to have a very bad time training your variational quantum circuits. And so this is also why it's good to know, okay, for which kind of circuits will I have this problem? Then also overparameterization, which is kind of the other side of this. So this is something that I've worked on in my PhD, is sort of the opposite phenomenon where, well, if you have polynomially sized dynamical Lie algebras, then you can very efficiently train these circuits. And so that's ideally the regime that you always want to be in. So it again goes to this point, maybe, yeah, it's good to know when these things are polynomial. Yeah. Yeah, okay, so there's a subtlety there. So the classical simulatability is only true for observables that are also, that have support on the algebra. So yeah, there may still be cases where you have a circuit that has a polynomial size DLA that doesn't, or that will allow you to do things that you cannot do with a classical simulation. So there's some, it's like a larger set basically. Okay, so then, and then finally, also some things I've worked on is like making these funky quantum gates. And there you can also relate the size of the dynamical Lie algebra to the complexity of calculating gradients of your variational circuits. So this is basically to say there's a bunch of different reasons in like quantum computing control, quantum machine learning theory, why you would want to know what these things are. And so this gave me a lot of questions because, as I said, I was curious, are there polynomially sized ones that we don't know of yet? Because only sort of a handful have been studied in the literature up to this point. Are there things between exponential and polynomial? Can we maybe just find all of them somehow? That should be very, very hard, but these were kind of the questions I was struggling with. And then I found these amazing collaborators that helped me tackle this question. And so, yeah, the point of the classification is, can we maybe find which Hamiltonians or which dynamical Lie algebras are out there in the wild? And can we just do it from a mathematical point of view? Yeah, and sort of describe all of them. So that led us, yeah, to this project. And there have been, as I said, other classifications like this. So this is one by Cartan that's from a long time ago, very, very beautiful math. Then Dinkin also had a classification in the 50s that was about maximal subalgebras of SU2 to the n. And then so when I went to the math professors, like, with this question, it was like, this is not something you're going to answer in a short project. It's an extremely complicated, deep mathematical question. So we should put some constraints on this problem, make some assumptions, and then maybe a sort of more tractable version of this problem we can then solve. And so this brings me to your question, like, okay, we need to make some assumptions in order to make this tractable. So the first one I already alluded to, we consider n spin 1/2 systems, and all the Hamiltonians are going to be some linear combination of Pauli strings. So yeah. Then we do not care about the coefficients in the Hamiltonian. So if we have a Hamiltonian that's just a Pauli x or 1/2 times x, we're just going to see these as the same thing, which as a physicist might hurt you a little bit because obviously the order parameters of your physical system greatly change the physics. But this is basically something we cannot really see on this Lie algebra level because we only care about commutation relationships between the operators. And yeah, we don't necessarily care too much about how strong one is versus the other. And this would be a very interesting follow-up direction, but I really don't know how you would include that here. Okay, so this is to your point. So we only allow these individual Paulis and not linear combinations. And the reason for that is basically because the Paulis form an orthonormal basis for all Hermitian matrices, and that makes the math a much easier. And if you allow for stuff like this, then the sort of space of possibilities just completely explodes and you cannot basically do anything. So then this is a sort of more physical constraint. So we only look at Hamiltonians in 1D, so chains or rings. And then this is a sort of a peculiarity that we're also able to prove. If the system is fully connected, then we can also do this classification. And then we only allow 2 local interactions, which is also sort of physics inspired. So this is kind of the setup. I hope this is kind of clear. Yeah. So it's basically if you have a bunch of spins and they can all talk to each other. Yeah. So I think if you have like, what is that with ion traps? I think you have like all-to-all connections. So that's kind of, that will be kind of this case.
This is 1D.
Sorry?
This is 1D.
1D means like, but the spins only talk to each other in like a, wait, let me, like this. So they are aligned on a line, or they are arranged on a line or on a ring. And then this is this all-to-all connected one. And yeah, we indicate these different types with a circle, and a pi. And so to give some examples, this would be sort of the most simple thing you can do. You have local fields on all of your spins. And then, well, all these things are independent. So the Lie algebra would be the direct sum of U1 algebras.
So if it's also connected, what does it mean to be 1D?
Also, okay, so that would not be 1D. Yeah. Yeah, so it's 1D plus the all-to-all connected.
Also, like the treating both cases.
Yeah, it's doing separately. Like we need to use some other techniques to do this one, but it kind of, yeah, it was kind of a peculiarity that somehow the techniques we use there allowed us to also quickly do that one. So we included it. Yeah, yeah. Yeah. Well, so there's still only two locals. So this one only talks, so that it's like an interaction like this, like this, like this. It's never like a 3-qubit or 3-spin interaction. Yeah. So yeah, it will be like if you have x1 tensor x2, x1 tensor x3, x1 tensor x4, like that. Like those would be this separate terms. So there will also always be two locals still, but they would just cover the whole system. So maybe maybe it's not local. So yeah.
The graphic sense, right?
Huh?
Local in the computer scientist sense, not in the physicist.
Yeah, that's I think the right thing. Okay, so let me give another quick example. So this was also already known that if you have the transversal Ising model on a ring, then the dynamical algebra of that will be this 2 copies of SO2n, which some of you may have seen before. It's closely related to like yeah, okay, let me not go deeper into that. But yeah, this I think has also been shown before. And then as a final example, maybe you have the Heisenberg model, and you put it on this crazy graph, and then, well, we, in our classification, were able to show that it's this SU 2 to the n minus 2, and then 4 copies of it. So this is kind of the goal of like, okay, you give me a Hamiltonian, you tell me which of these topologies it's on, and then I can tell you, okay, the dynamics will be in this Lie algebra or this Lie group. And so, yeah, then the sort of statement of the classification is, what are all unique dynamical Lie algebras of translation invariant to local spin Hamiltonians in one dimension? And the translation invariant part means that basically you have the same interactions on all the bonds. And so, yeah, this is the idea of like, can we somehow make a circle around these things that are already known and fill in what is sort of out there and what can exist in this sort of restricted space. Where I should mention that this is not to scale, this is much larger than our little circle. Okay, so then what is the strategy for this? So it's actually somewhat straightforward, at least in the beginning, because what we do is we start with just looking at 2 qubits, because we only have these 2 local interactions. So we identify all the unique dynamical Lie algebras on 2 qubits by sort of a brute force enumeration. And then what we do is we add sides slowly, and then we see how do these algebras change and which ones become equal to each other and which ones sort of stay unique. And here we can actually rely on the very nice result of Cartan, which basically says that any of these dynamical Lie algebras will be some combination of SON, SPN, or SUN with some trivial center, which is this semi-simplicit or semi-simple condition, basically. Yeah.
Curiosity, do you think about, like, when you have the whole space of dynamical algebras and you have the subset that have your assumptions, how much smaller is the subset?
Well, it would be probably well, it's kind of hard to tell because you don't know. I assume it's much smaller because I think you can have Hamiltonians with 3-qubit interactions, 4-qubit interactions, all the way up to n. And like there's so many different constraints you can put, but maybe all of those would just give you SU2 to the n. So maybe they're all boring, but I think that's kind of hard to say.
Nice.
It's just like it becomes immediately interactable as soon as you go to, say, 3-qubit interactions.
Nice.
So at least with the techniques that we used here. But yeah, I assume it's much larger. Because I think I remember, I think all the sub-algebras of SU, let's see, maybe it's SU6 or something, those have been classified. Like it's a very hard mathematical problem to sort of take them all apart and yeah. Yeah. Okay, so then how do we do this? So the first step is kind of easy. So there are 15 Pauli strings on a 2-qubit system. We generate the power set of all possible Hamiltonians that you can generate with these. So that gives you 32,767 Hamiltonians. And yeah, here this is some more notation. So this is kind of the 2-qubit Hamiltonian. And this set of generators are basically the types of Pauli. So this would be, oh wait, I think I have a nice thing here. Oh yeah, so in this set, you would, for instance, see this local field one. You would see the transverse field Ising model sort of terms. And then also this like super whack Hamiltonian that probably has no physical meaning at all. But it's still in this set. So okay, so then we have that. So then what we do is we start doing this nested commutator thing. So these are generators. They don't actually give us the Lie algebra. So what we need to do is we need to take all these nested commutators until we can no longer do that. And then we get some Lie algebra, which for a 2-qubit system, you can just kind of look at the generators, or sorry, look at the elements that you get. And then you can see, oh, it's SU4, or it's SO4, or SP2, or whatever. So for these, for this step, you just run some algorithm, you input the generators, do the nested commutators, and then you get 146 unique ones. So it's already kind of a drastic reduction from this big power set, basically. Then what you do is you realize that the Pauli matrices have lots of symmetries. In particular, yeah, so you have this Z2 symmetry, which is because we have a 1D system, it doesn't matter if we do IX or XY. So this is kind of a sort of a physical symmetry. And then this S3 is, it doesn't matter if you have, say, an XX term or a YY term or a ZC. It's just some choice of bases, basically. So we can take those out. So this is like a simple example again. Okay, we have this XX plus YZ, YY plus ZX. And then if we relabel, then we actually see that they're the same. Because, yeah, because Y goes to X, yeah. So then we know that, okay, we can just take one of these, yeah?
Counting graphs of these?
You need commuting graphs?
Yeah. Calling
Uh-huh.
and how counting graph of this.
Mm-hmm.
This means that these 28 graphs are empty.
That would be another way to do it. Yeah, because that's probably 1-to-1, and then there you could do like say that the graphs are equal, so then the algebras must be equal. I think that we actually do use these frustration graphs at some point in the proof to sort of show some of these isomorphisms, but that's a good point. Yeah. Okay, and this is that two symmetry. This is what I said. Like it doesn't matter if you have xx plus yz or xx plus zy. Yeah, all that matters is that these two terms are the same. So if you flip the sides, it's the same thing. Yeah.
Does this S3 reduction breaks down when you allow the coefficients? Yeah.
Probably, yeah. So then you already see, then you have to deal with maybe 60 more, and then you need to do individual proofs for 60. Like it just becomes very hard. Yeah. So, okay, then after this whole process, we're left with these 28 unique ones. And then actually the hard mathematical question sort of begins, because now we need to know what happens when you go to n equals 3, 4, 5, 6. So maybe this fifth algebra, that's like number 5 out of these 28, on 2 qubits, we can say, okay, it's SO4. But then we want to know, okay, when we go to 3 qubits, what is it? And here you need to do some sort of inductive proof to sort of show how this algebra will grow. And this, I don't think, well, I don't have time to explain. It's pretty involved, but a sort of sketch of how you would do this is that, well, for the linear ones, it's kind of simple because you keep having just direct sums. Then you have these quadratic DLAs. Here we use these frustration graphs. So as you mentioned, you basically look at the anti-commutator graph of this algebra, and then you can sort of prove how it will grow as you go to larger n. And then you sort of look at this graph, and you can say what kind of algebra it is. The trickiest one are these exponential DLAs. So there's I think maybe 15 of them, and there you need to do some pretty complicated proof that I don't think I can quickly explain. But yeah, that's sort of the setup is basically you can do it with a computer, and then this you need to do some actual math. And then what you end up with is this list, which is kind of, I think it's kind of nice because it's basically a proof that there are 17 unique dynamical Lie algebras for open chains. And then, I mean, there's 2 other tables for the periodic one and the permutation invariant one, but I just wanted to show you this one. So yeah, they're enumerated. And then for some of them, you can see that depending on if they're even or odd, or maybe they're cycles of 3 or of 6, of 8, you end up getting different types of algebras. But as you can see, they're all sort of direct sums of ones that we know of. And just to highlight some of these, so most of the Hamiltonians that you generate with this procedure will be universal. So they will give you a controllable system or a universal gate set. Then this SON one and SO2n minus 1, these are the transverse field Ising model and / free fermion systems. We have this XYZ model, or like the Heisenberg Hamiltonian. Then these like symplectic groups shows up, which can be related to quadratic bosonic systems. So yeah, you can sort of find some of these physical systems back in this classification, but then there are also these completely crazy ones that, well, we're not really sure if they correspond to anything physical or if they're useful for something. But if you wanted to make a circuit that lives in SP 2 to the n minus 2, I can now give you the Hamiltonian that will do that for you. So the sort of sad thing to me here was that, yeah, we basically get these 3 classes, which is also like, well, how these 3 proofs were split up. So the linear ones, which are the sort of trivial, the quadratic ones, which unfortunately only contained the ones that we already knew of. So the free fermions and the transverse Ising model are basically in here. So there's no other system that lives in this class. And then all the rest of them are exponential. So yeah, I was kind of disappointed by that because I was hoping for some exotic thing to show up here, but maybe these constraints are too strong, and yeah, this is just what you're gonna get. And this picture is kind of the same for the closed chains and the permutation invariant system. So there's nothing really, yeah, some exotic scaling here, unfortunately. So then in the rest of the paper, what we did is we basically confirmed some of these things from the literature using the algebras that we found. So these are ones that people haven't studied before, like these A8, A7, A11 are some like exotic Hamiltonians. And same for these, and we show, okay, this barren plateau results hold, and this overparameterization effect holds, and well, the circuits that you get when you use these algebras actually live in sort of the space that you expect them to live in. So this is kind of the sort of numerical aspect of this paper. We just checked these results from the literature to our classification. So then, yeah, that's sort of the 1D classification. And maybe, I think when we finished this, I thought, okay, what if we can we do 2D systems now? Can we do some other more exotic topology? And then initially we were like, oh yeah, surely that's going to be harder because yeah, there's so many different ways in which you can construct different graphs. But actually, as it turns out, the non-1D case is extremely, well, I wouldn't say boring, but it's not as interesting. So in the follow-up work, we asked this question. So if we have now two local Hamiltonians on any sort of graph, so now, yeah, you can choose the connectivity however you want, but there's still the constraint that these interactions all need to be sort of the same two local Paulis. So the sort of same set of Hamiltonians we considered before. Then you can prove again what all the dynamical Lie algebras will be. And the only defining characteristic is whether the graph that you've constructed is bipartite or not. So again, this proof is kind of a lot, but this is sort of a sketch. So you have a flow chart that basically tells you, okay, you look at your graph, is it bipartite? If yes, then you go through this route. If no, you go through this route. And then based on that, you get different types of dynamical Lie algebras. And again, to me, the sort of sad note to hold to this is that they're all exponential. So there's no interesting quadratic ones. Yeah. So this is kind of, I think, an interesting, yeah, result because the 1D case is very special and everything else is kind of looks the same, at least from this picture. So yeah, then maybe let me talk about some of the consequences of this. So I kind of alluded to this already in the introduction, right? If you're doing variational quantum computing, what this classification will tell you is that if you make a circuit with 2-qubit gates, any type of circuit with 2-qubit gates is basically contained in our classification. They will always have barren plateaus because all the DLAs are exponentially scaling, except for this very small class of free fermion circuits where you can have this overparameterization phenomenon. And so that is kind of a bleak statement because it basically says that there's only one class of circuits that you can train efficiently. Which, yeah, I've struggled a lot with just the barren plateaus in my PhD, and I'm kind of a more optimistic than what these results will tell us. So to end on a more positive note, I will ask this question, which is, are barren plateaus actually an issue? Or should we maybe not care about them that much because, well, they're typicality statements, and in practice, maybe we shouldn't care too much about those. And there have been some work, so Wiersema and I have done this work where we train variational circuits on 80-qubit systems, so where this barren plateau should be extremely severe. And then we find that with some clever warm start techniques, you can actually sort of get around these issues, and you can still like optimize very well to some very low cost and get sort of the result that you need. And yeah, there's this paper from Zoe Holmes' group that is more theoretical, but they also give some strategy for doing warm starts for imaginary time evolution and showing that under some conditions you can use this to maybe get around some of these problems. So I'm more of a believer in this, but yeah, the time will tell whether this can actually solve some of these issues. Yeah, and with that, I would like to conclude. So yeah, I think these classifications can serve as hopefully a backbone of other work. So right now, if you're doing any sort of quantum info stuff that relates to the special unitary group in some way, then I think our classification will allow you to make statements about sort of this whole class of dynamical Lie algebras. So as long as you're doing anything with a semi-simple group, or with Hamiltonians that look like the ones that we have, then all your results, I think, should apply to this whole class in one big go. And I think that's a very powerful sort of tool that we now have. And then for the future, yeah, coefficients, linear combinations of Pauli's, this would all be very exciting. But I don't know if you can actually do any classifications because sort of the space just becomes so massive, and I think it will be hard to sort of reduce this to something tractable. And then, yeah, finally, can we go beyond this dynamical Lie algebra picture because it is very coarse. Yeah, because a lot of things kind of look the same, even though there can be many sort of microscopic differences that can have like very large effects. But we cannot really probe that with this view because we only care about these commutators. And there's some work in this direction going on right now that I'm pretty interested in. So yeah, hopefully that will allow us to make more interesting statements. So yeah, that's it. And these are my amazing collaborators. Again, Professor Bakalov was responsible for the mathematics. I like all these proofs. He's very prolific, and I have him to thank for writing a 40-page appendix on this. Yeah, and that's it. I don't know if you have questions, but yeah. Yes. Yeah.
So you said earlier that it doesn't really matter if you have coefficients because it doesn't show up in the algebra, algebra. So why would adding coefficients, like you say here in your conclusion, or something to do next, would that not just not make a difference again?
Well, so I think the idea would be that you could consider things like maybe this one has a coefficient A, and then this is a coefficient, something like that. So then I think it's kind of, maybe I'm kind of talking about the same thing where now this is one thing, this is one thing. So that would be the way to incorporate coefficients by basically saying, yeah, we treat these on the same level and this one on its own level. Yeah. Yeah. Yes.
Say go beyond dynamical Lie algebras. What would be the other object that to classify Hamiltonian?
So okay, so so what in this paper by Max West, he basically looks at let me think about this. He basically looks at what are the sort of spaces you get when you calculate these nested commutators. So maybe so you have, say, you start with these two generators. And then, well, what we're doing with this algorithm to generate the DLA is we take all the nested commutators until it closes. But what you can imagine is you have basically different levels. So you can, on the first level, you get two new terms, which are A and B, which let's call that C. Now, on the second level, you get A with C, which we call B, and B with C, which we call E. And so, yeah, you can basically make a graph starting from your generators that will sort of generate new Pauli's as you keep adding more and more brackets. And so it's kind of some sort of scrambling yeah, some sort of scrambling of this bracket. And so that gives you a more fine-grained view because it will tell you how quickly are you in this limit of yeah, something that's dense over the group, basically.
You kind of take the normal DLA and you attach the number of which layer
Yeah, exactly, yeah. And that will allow you to say something about, yeah, like I think like information scrambling, because it will tell you how quickly things will propagate through your system. And it's still related to the DLA because you sort of know at the end what you're going to get, but it's maybe how you get there that can give you, yeah, interesting information. So yeah, that would be, yeah, and there's some work on this. But I think all our stuff would still be sort of on top of that because you would basically know what classes there are, and then yeah, you can do this for these 17 algebras that we find. You don't need to look at anything else because they're all isomorphic. So
you say you can only add information that makes like, study something that is less
yeah,
strange than the other.
well, yeah, I think something like this, like I think these are called G modules or something like that. That would be it. Yeah.
Really good though. I want to know what step made it hard to go to like 2D volumes or higher dimension.
What made it hard or easy?
Yeah, like where like this proof that you had like you do not use or like you cannot apply the stuff.
Well, so I think okay, so this result, this one basically means we can do any topology, so 2D or 3D graphs all work. I think what gets really hard is if you allow like stuff like this. Like if you're sort of starting Hamiltonian can have 3 local terms, then you get I think I calculated how many Hamiltonians, but basically in this first step here, then you get 2, let's see, how many Pauli strings do you get? 2 to the 4. Yeah, you get 3 to the 4 Pauli strings, and then you need to take the power set of that, and that is a very, very large number. So you cannot brute force enumerate them, but then you probably have to switch around some of these things, like you need to already reduce the symmetries when you generate them. Maybe that could be done, but I think we looked at it briefly and it was like, that's probably hard. And also maybe from a physical point of view, maybe 3 local interactions aren't that common. So it would really be mathematical exercise and maybe not that useful for the practical, yeah.
Any more questions? Well, if there's no more questions, let's thank the speaker again.